Hi, I'm David Bonzak, Product Manager for Rheology at TA Instruments. I'd like to welcome you and thank you for joining us for today's webinar. If you get disconnected at any time, please use the instructions you received to log back in. You can access various content by clicking the Documents widget at the bottom right-hand corner of the screen. This includes speaker bios and additional file downloads. If you need help at any time, click the question mark widget. Please ask any questions you may have at any time during the presentation by submitting them through the Q&A window. We will answer as many of these as possible at the end of the webinar. Our guest presenter today is Professor Gerald Fuller, who is the Fletcher Jones Professor of Chemical Engineering at Stanford University. Jerry has been teaching and leading research at Stanford since graduating from Caltech in 1980. Professor Fuller's research has centered on three areas of rheology: optical rheometry, extensional rheology, and interfacial rheology. These experimental efforts have been aimed at a wide range of soft materials that include polymer solutions and melts, liquid crystals, suspensions, and surfactants. A more recent focus of his work has been linked to biological materials. Professor Fuller received the Bingham Award from the Society of Rheology, for which he is also a fellow. He is a member of the National Academy of Engineering and the American Academy of Arts and Sciences, and is currently serving as the General Secretary for the International Committee on Rheology. Today, Jerry will present Interfacial Rheology, a fundamental overview and applications. It's a real pleasure to have Professor Fuller with us today. Jerry?
Well, thank you very much, David, for the very nice introduction, and I'm delighted to be here at TA Instruments in Delaware to offer this webinar on interfacial rheology. Now, in 2013, I offered a version of this that I invite you to go to the TA website catalog and find it, because in that first webinar, you'll find a lot of background material that I won't cover in this webinar. I'll be primarily jumping to applications of how interfacial rheology can be used. So up on the screen, you'll see the workhorse of interfacial rheology that we use in my laboratory and in many other laboratories, and that is the double wall ring. It's attached to a DHR TA rheometer, a very sensitive torque transducer. And so let's start the presentation. So liquid-fluid interfaces, that's what we're talking about, and they surround us. We find them in foams, emulsions, and coatings. We find them in our bodies. We have the tear film of our eyes, the alveoli in our lungs. These are fluid interfaces that can easily and readily deform. Now, we classify these fluid interfaces into one of three areas. Simple interfaces are what we learned about as undergraduates in fluid mechanics. These are interfaces that cannot sustain a surface stress. They are characterized by surface energies and tensions, but these are thermodynamic quantities. They're not rheological. Moving up, you have what we call Newtonian interfaces. These are interfaces that can support a stress, a in-plane stress, but the relationship between that stress, surface stress tensor, and the deforming action of surface gradients is a linear one. Just like a Newtonian liquid, we have Newtonian interfaces. And finally, at the most complex level, we have interfaces that do support stresses, but the relationship is highly nonlinear, and we need to make rheological characterization of those interfaces. And those are the most common examples. So simple liquid-fluid interfaces, such as just the surface of a glass of water, characterized by surface energy, shown here in this simple equation as sigma. Surface energy is energy per area. So U is the intermolecular potential between molecules in the liquid, in the bulk, but at the surface they're robbed of some of those interactions. And if we imagine that those interactions have an energy of kT, this thermal energy, we can estimate the energy per area by simply dividing by the mean area. So if the molecule has a diameter of d, we'll just take d squared as the area. So that's a reasonable rough estimate, and it's quite accurate for nonpolar simple hydrocarbons. You'll get about 30 to 40 dynes per centimeter, or ergs per centimeter squared. And that brings it the point that the surface energy has the same dimensions as force per length. And so that's why you sometimes refer to it as a tension. On the other hand, water with strong hydrogen bonding interactions has a very high surface energy, about 72 dynes per centimeter. Now, a complex fluid interface can support a stress, and you can see that here. This is a pendant drop of water dangling from a syringe, but it's inside decane. And attached to the surface of that droplet are ellipsoidal particles. These are micron-sized particles, and they've attached to the surface. And you form sort of an eggshell viscoelastic skin on the surface of the drop. And so when you withdraw liquid into the syringe, you get a wrinkling. You can see that on the most left, on the most right image there. You can see the wrinkling of that drop as you withdraw liquid into the syringe. So clearly, we need to have more sophisticated tools to try to represent the rheological character of these interfaces. So here is an example, again, particles interfaces, but there are many as I'll go through. Here you see the reason why you get this rheological complexity. You have particles in this demonstration, polystyrene, 3 microns, adsorbed at the interface between decane and water. Now let's shear that interface. And you can see that you're distorting the arrangement of the particles. You've changed the microstructure. And that's the origin of the complicated rheology, interfacial rheology of these sorts of interfaces. And they're all around us. They come to us from biology. We have the bilayer, the lipid bilayer that creates the cell membrane. Imagine if a cell then deforms in the process of dividing, you're going to deform that interface. And so the relationship between that deformation and the stresses is important. The tear film of our eyes, that's a very important, very thin, micron thick layer of water and protein, but you've got to stabilize it, and that's done by a lipid layer that's spread when you blink. Likewise, in our lungs, we have the alveoli, and the body produces a special surfactant that helps stabilize that layer. Biofilms are very important to human health, and these are very complex mixtures of amyloid fiber, polysaccharides, and protein that the bacteria produce to protect the colony, and I'll go into more detail about that in an application. And then we have industry and the environment. We have foams in the foods that we eat, such as ice cream, or emulsions in the salad dressings that we use. But unfortunately, if you have a water spill, an oil spill on water, you can create a very tenacious emulsion that's whipped up by wave action. And if there are asphaltenes in that oil, they'll stabilize those oil droplets and water droplets that are formed to make it very hard to clean up the mess. So, it becomes very important for a number of reasons to properly characterize these very, very nonlinear mechanical responses that we have for these types of interfaces. So why does it matter? Well, now if we try to actually predict the behavior of a, let's say, a water droplet that is coated with asphaltenes in crude oil that we're trying to refine, we have to get rid of that water. Well, let's try to predict the behavior of that water droplet. Well, that's a complex fluid mechanical problem. I show you some of the challenges in this slide here. You've got the two fluids, oil and water, and they are described by equations called the Navier-Stokes equations that allow you to predict the stresses in those liquids. And then you have the interface between them. And that means you need to invoke what's called a boundary condition that connects the stresses from fluid 1 through the interface into fluid 2. And in just below the figure, you'll see a long equation where tau ij superscript 1, that's the stress, the bulk stress in fluid 1, minus the bulk stress in fluid 2, but evaluated at the interface. So that's a stress difference. And that stress difference has to be supported by the interface. So the other two terms involving capital gamma are coming from the interface. Capital gamma is the stress tensor at the interface. And the first term is the gradient in that stress. And then the term on the other side of the equation, those are arising from normal stresses. But we need to know something about that interfacial stress tensor. So we have that differential element on the left-hand side, the differential of that interfacial stress. That is a result, that is an in-plane contribution. Very important. Even the absence of rheological complexity, you have what are called Marangoni stresses. And that's where they come from. And then you have, on the right-hand side, these normal stresses. And in the absence of rheological complexity, that gives rise to something called the Young-Laplace equation. But we need to have a constitutive model, and that is, what is the relationship between that stress tensor, capital gamma, and the deforming action on that interface? Well, that's a constitutive model. The simplest one is a Newtonian one, and that's where that relationship is simply linear. And I show you it here, and this is the Boussinesq-Scriven model, very famous equation. And you can see the linearity between capital gamma and the velocity gradient, dUs. US is the velocity at the surface. That's a linear relationship. Capital D is the rate of strain tensor, also linear in US. And so you see that linearity. Now there are two parameters in that model. Mu sub s, that's the surface shear viscosity. We would like to measure that. And the other one is kappa sub s, that's the surface dilatational viscosity. That has to do with the fact that interfaces can expand and contract. If you eliminate mu sub s and kappa s, all you're left with is something called capital pi, and that's something called the surface pressure, which is essentially coming from the surface tension. We want to have rheological instruments that can help us measure these material functions, surface shear viscosity, dilatational viscosity, and other quantities. So let's talk about interfacial rheology. The very top line is the surface tension or the surface energy, and that we measure in it with a number of very old classical techniques. Now, what we actually represent normally is the difference between the surface tension of a clean interface and the surface tension when you've got it covered with some surfactant, let's say. That difference is positive, and that's called the surface pressure. But now let's talk about a rheologically interesting surface, one that can support a stress. And let's now deform it in shear. That's constant area. And if it's a fluid interface, the rate of deformation will give rise to a surface stress, and that's where the surface shear viscosity comes from. But I can also expand and contract that interface. And if it's a fluid interface, the rate of deformation gives rise to a dilatational viscosity. I'd like to measure that. On the other limit, you can have a very elastic interface, and you would then have an elastic shear modulus, G sub S, a superscript S, and a dilatational modulus, E superscript S. So these are the quantities it would like to measure. But in reality, as you can see here, we never have anything that's purely viscous, only a viscosity, or purely elastic, only moduli. We have everything in between. We have surface viscoelasticity. And that's captured by a very important rheological technique. It's called dynamic rheometry, where we oscillate the deformation in time. And at one limit, the stress and strain are perfectly in sync. That's an elastic interface. On the other limit, they're out of phase by 90 degrees, and that's a viscous interface. And so, as you can see in the equation tau superscript S, that's the stress at the surface, it's either proportional to a sine wave, that's the in-phase part, or proportional to a cosine wave, that's the out-of-phase part. And there are two moduli. You have the surface elastic modulus, G prime, and the surface viscous modulus, G double prime. And you can see an example below where you plot these moduli as a function of that frequency. So we'd like to measure the surface viscosities. We'd like to measure surface moduli. And you can do that very successfully with the double wall ring interfacial rheometer, shown here. This allows you to take a rotational rheometer and convert it into an interfacial rheometer. And you can see here the DHR hybrid rheometer produced by TA Instruments is a very sensitive instrument. You need a sensitive torque transducer, such as this instrument has. And then mounted on it is a patented accessory by TA Instruments, and this is the double wall ring. You can see it's mounted right on, and this allows you to take your very expensive machine, this rheometer that you may already have, and convert it nicely into an interfacial rheometer. So let's look at it in detail here schematically. You can see the ring coming down, and it rests inside the interface. And it sits there, and there are two interfacial gaps on either side of that ring, and that's why this mimics what's called a double couette. When you rotate that ring, you shear the interface on either side of the ring. And measuring that torque, you can convert that into a surface stress. You can then pour, let's say, water, usually on the bottom. It's more dense. And if you're interested in an oil-water problem, you could pour your organic phase on top, and then you would have interfacial species that would absorb onto the interface and render that interface complicated. Now, when you make these measurements, you have to bear in mind that it's intrinsically impossible to deform an interface without deforming the bulk phases above and below. So it's important to construct what's called the Boussinesq number, and that's the ratio of the surface viscosity eta S divided by the bulk viscosity, A to B, and then divided by the diameter of some object that's creating the flow. In this case, it's the diameter of this ring. So this ring that we use is very, very slender because we want the Boussin's number to be large. So as opposed to the bicone, where you don't have a small dimensional group, you've got a very large one. With the double wall ring, you can get very large Boussin's numbers and amplify the importance of the interfacial signal. Now we're going to go into applications. So again, I invite you to look at the earlier webinar where we go into a lot more detail about background on capillarity, for example. I'm going to go into 4 different applications. The first one has to do with biofilms. And these, again, are around us. They're actually inside us, unfortunately, because they're associated with infectious disease. So they can be present. They like to attach to surfaces, such as a catheter, unfortunately. But they'll also attach to liquid air interfaces, even in our body. And this shown here, you can see that you have in the schematic on top the bacteria, these gray bodies, and they're exuding fibers. Amyloid fiber, these are misfolded protein, polysaccharides, cellulose, and other proteins. They come together to form a viscoelastic network. And this protects the colony against external influences. They love to attach to surfaces, and so on the right you can see these wonderful morphologies that are either grown on a solid support on the upper picture, or below you can see it growing on the surface of a colony in an aqueous media and air. In that case, they're called pellicles. But they grow everywhere, and they grow in our bodies, but they can also foul the hulls of ships. They can foul the internal parts of plumbing fixtures. They're a problem. So it's important to try to measure the viscoelasticity of these biofilms. In the form of pellicles, it's straightforward because we can now use the double wall ring very effectively to measure them. And we've studied a very important bacteria that's responsible for cholera. So cholera grows in aquatic environments, and if you have contaminated drinking water, people can, even still today, be affected by cholera. We were interested in trying to understand which elements of the biofilm contributed to the viscoelastic strength of the biofilm produced by this bacteria. So we collaborated with biochemists that were able to produce a number of mutants, and you can see them on the pictures at the bottom. Rugose is what's called the wild type. That's what grows naturally. And that's what the visual appearance of the biofilm in that case. Whenever you see a delta, you've knocked out a protein, and there are 3 of them: RBMA, BAP1, and RBMC. And you can see single knockouts, and then the 5th photograph is a double knockout, as is the next one and the next one, and finally even a triple knockout. So how do we make this measurement of viscoelasticity? Well, we use a double wall ring, shown here. Now, biofilms take forever to grow, and so we needed to modify that double wall ring cup so that we could keep the level constant in spite of evaporation. And we did that by not only having one inner region where the ring sits, but an outer one, which we continually fed with broth, and we simply used Archimedes' principle to keep that level constant. And you can see the schematic on the left here where we pump media in, suck it out, but there's a communicating orifice between the two regions. And then we use the DHR rheometer from TA we oscillate the ring, and we measure the relationship between stress and strain, as I mentioned before, and we get two moduli, G prime, the elastic modulus, and G double prime, the viscous modulus. And we track those as a function of time. And you can see them here for the wild type, or the rugose. And look at those time scales. G prime, we're only tracking here the elastic modulus. We also measure the viscous, but the elastic is the predominant modulus. The time scales are very long. We usually get a local maximum, and that's accompanied by a wrinkling of the interface. It's a mechanism where the interface relaxes some of the stress by wrinkling. So the upper left is the wild type, and then we compare that data to the dark circles where we've knocked out RBMA, one of the proteins. There certainly is a shift in the data. It takes longer, but it still grows. When you knock out BAP1 protein, it doesn't recover. You knock out RBMC, it recovers, and so forth. And in fact, if you look at every instance where we've knocked out BAP1, delta BAP1, or a double mutant where one of the mutants knocked out is BAP1, or the triple mutant, those all have unrecoverable diminutions in the modulus. So we think we found the principal protein responsible for the tenacity of that biofilm associated with cholera. So that's one application. Now, the nice thing about this attachment is it allows you to do some chemistry. This attachment is sold with the ability to pump liquid in and out of the cup and maintain the level fixed at the position of the ring. So you can do chemistry. So you can bring in a molecule that might interact with your interface, and you can track that very nicely. We looked at a different bacteria, an E. coli. It's uropathogenic, so it'll make you sick. And we looked at several molecules that upregulate biofilm production. DMSO, it's often used in hospitals. Does it have an effect on biofilm? Ethanol, it's often used to our enjoyment, but it's also used as a cleansing solvent. So these are known to promote biofilm production. We wanted to see if we could see that in our rheology experiments. There's a downregulator, curcumin. Curcumin is a chemical that you'll find in curry. Okay, so that's interesting. It's thought to affect amyloid-related diseases. For example, it's been recognized that there's a lower prevalence of Alzheimer's and Parkinson's disease in the Indian subcontinent, where a lot of curry is consumed. So there's that idea, but how does this molecule affect biofilm? We can test that. So here are the results. We're plotting on the vertical axis the surface elastic modulus, and then you have time in hours. The wild type is the blue curve, and you can see there are two growths. The first growth is just attachment, arrival of the bacteria to the surface. And then you get a second one after about 30, 40 hours, and that's the creation of the biofilm. Now, let's add DMSO at 2 and 4%. That's the green and the kind of the red squares. You can see a very dramatic increase. It happens earlier, and it's elevated in strength. And that's a log axis on the modulus. Ethanol, same thing. You get the biofilm occurring earlier by about 10 hours, and it's stronger. If you knock out the ability of the bacteria to produce biofilm, you can see that the lowest curve, the light blue. So that's what happens when the bacteria gets to the surface, but there's no biofilm formed. What about curcumin? Those are the light brown colored circles. Complete lack of biofilm formation. So that's interesting. So evidently, the parents of Indian children know what they're talking about. Eat your curry, but not so much alcohol. So, but you can find this out very nicely with this attachment, because you can do chemistry. You can introduce chemicals you want to find out about the interaction. What about interrupting biofilm formation with the addition of a surfactant? So surfactants are used a lot in the pharmaceutical industry to try to avoid interfacial problems. So we have a collaboration with Genentech, and they're interested in this problem. They make proteins in the form of monoclonal antibodies. They want to make sure that they avoid issues surrounding that protein absorption. But here we've got biofilms attaching to a liquid-air interface. Can we use a surfactant to interfere with that? Polysorbate, tween 20, is a surfactant that's often used, and it's shown pictured here. So let's look at its effect. You can see here the surface modulus is a function of time. The light blue is no surfactant. The light brown, you've added just the tiniest amount. It's what, 0.0001% tween 20. Increase it to 5, and that's the green. It's shifted. It delays the onset of biofilm production. And then if you go up to 0.001%, you've postponed it to about 90 hours. You're also diminishing the magnitude of the modulus. And if you plot the modulus, magnitude is a function of tween 20 concentration. You see it plunges to 0, coincidentally at the level of concentration called the critical micelle concentration. So again, this is a way, using this instrument, to do some chemistry and to systematically vary the concentration of chemicals that you might want to interfere with interfacial viscoelasticity. Hydrates. Now moving into the oil industry. Hydrates, they're a big deal in the oil industry. Forms at the interface between oil and water. And you can see the problems that they cause. On the picture on the lower left, you can see a hydrate plug that has completely blocked the production of oil. And it's kind of an ice-like structure. And unfortunately, in the Gulf of Mexico, hydrate production is strongly implicated in the disaster that we had several years ago. So it's important to understand this interaction between oil and water. So what is a hydrate? Well, it's a hydrogen-bonded cage which envelops hydrocarbons. Normally, it's natural gas. Happens at cold temperatures and high pressure. So this is particularly important offshore. So in Brazil, for example, very concerned about hydrate production. So you can see on the bottom a simple schematic of a phase diagram where at high pressures, cold temperatures, you get hydrates. If you move up in temperature, lower the pressure, they go away. Okay, so it's an interaction at an interface between water and oil. So how can we use interfacial rheology to test that? Well, in this initial study, which is actually performed in Rio de Janeiro, we used the fact that cyclopentane in water will form a hydrate, but at ambient pressures. So we can use simple room pressure conditions. And the hydrates form if you go below about 7.2 degrees centigrade. And there's the schematic of cyclopentane. It's a small molecule. Pentane by itself will not form a hydrate. By bending it into a circle, you reduce its size sufficiently that now you can trap it inside hydrogen bonds. Okay, so now how do we do this? Well, we need to control temperature, so we made a different cup. We made it out of brass. We sat it on a peltier so we can control the temperature. You can see the ring inside this double wall couette, and we show it now just with water in the bottom, and the ring is at the surface of water, and then we'll pour cyclopentane on top. And here is the instrument. You can see it on the DHR. Again, we're going to jiggle the ring slightly and follow the relationship between stress and strain and get the moduli. So here's how the experiment works. Plotting modulus as a function of time. And this was initially, this is data that was taken at 3 degrees centigrade. So that's below 7. So hydrates should form. Here's how you have to do the experiment, though. It's important to inoculate the system by having the cyclopentane touch ice. So here's what you need to do. First, the first 500 seconds, we just had water in the system, no cyclopentane, and no ice is formed. You have to go below 0, and you can see that when we go to -5, the modulus shoot up. We actually froze the water, and then between 500 and about 700 seconds, sometime in that time period, we poured the cyclopentane on top and then raised the temperature up to 3 degrees centigrade. And what happens is the water melts, the moduli drop to essentially 0, but then it starts to grow. We've inoculated the hydrate formation. You need that inoculation before this will actually happen. And you can then see G prime in blue and G double prime, the viscous modulus, in red, growing over the course of hundreds of seconds. So the first time you're able to actually follow the kinetics of hydrate formation. Once you've got it formed, you can do a strain sweep and see how strong this hydrate film is. So here are 4 sets of data. The upper left is at 3 degrees centigrade. That's the data I just told you. And there are 3 separate experiments. The upper 3 data, the red, blue, and green, those are the elastic moduli. The dots below are the viscous moduli. You go up to 6 degrees centigrade, and you can see the moduli are stronger. Up to 7, even stronger. But now when you go to 8 degrees centigrade, no hydrates are formed. So you've gone above that phase transition. So it's a very nice way to probe this. And you could, with the ability to bring in other chemicals, you could look at how to postpone hydrate formation. So this, again, this tool is very, very flexible. Here's a strain sweep, and you can see the moduli. The upper one is the elastic modulus. The lower one is the viscous modulus as a function of strain. And you can see at about 5%, 0.5% strain, you get a yielding of this hydrate film. So these are very soft, fragile films that are formed. So that's that application. Now let's look at another oil field problem, asphaltenes. It's a big problem also in the oil industry, from production to refining. So let's look at how this occurs. So it's a problem in production on the left, and refining. This schematic here is something called the desalter. It's the very first unit operation that you'll encounter in a refinery. And its job is to remove salt from the oil that's coming into the refinery. But asphaltenes can cause a problem. There's a schematic of one on the very right. These molecules are associated with heavy oils, and they're more and more frequently encountered as we work harder and harder to extract oil out of the ground. These molecules are polyaromatic hydrocarbons. They're quite polar. You can see the cyclic rings here, and then you have aliphatic tails. It has the appearance of a surfactant. In fact, it really is. It does have surfactant-like character. These are classified through a very crude analysis, solubility. These molecules are soluble in toluene, but insoluble in heptane. So you can extract them conveniently from oil, and you'll get a black residue that you can then resuspend for the purposes of experiments, as we did in our case. But these have a surfactant-like character, so we expect that they're going to love interfaces, and they do. They attach to the walls of pipe, and they attach to oil-water interfaces. So let's look at the desalter. You've got crude oil, and it's got some salt in it. To get rid of the salt, what they do is they actually add water and then mix it together to make an emulsion, bring that emulsion up into this really a settling tank, and now you have a liquid-liquid extraction with the water droplets slowly settling down through the oil. Salt from the oil will go into those water droplets, and now they have to coalesce. Well, if you have attached asphaltenes to your water droplets, you're going to create a viscoelastic skin that's going to retard coalescence. So you'd like to understand the influence of that adsorption. So here's the experiment that we created. We have toluene. Remember, our asphaltenes will dissolve nicely in that, and below it water. Then we add some asphaltenes, kind of ugly molecules. And then we change the concentration. We add a drop from above. Give it some time. They adsorb to all the oil-water interfaces, and then we bring the drop down towards that interface, and then we'll get a drainage. This is a thin film problem. In fact, most applications where interfacial rheology is important are thin film fluid mechanical problems, like in the tear film of the eye or in the lung. Thin film hydrodynamics. So we would like to then see how long it takes this drop to coalesce. So we've got some cameras, one on the side, and you can see the interface. Actually, we bring it up, and you'll see a slight curvature of the interface. You can't see the drop because once you put asphaltenes in the toluene, it's black. But you can see this depression. And that's that big drop coming down, and you're squeezing the toluene out. And that'll thin down, and the bottom camera then will start to pick up interference patterns. And you can analyze those interference patterns and measure the thickness of that film as a function of time. We also measure the pressure inside that drop. It first increases because we're increasing the hydrostatic head above the drop. And then we leave it flat, and that's the drainage. And then the pressure drops, and that's coalescence. And so that gives us a way of measuring the coalescence time. And we do that as a function of asphaltene concentration and aging. But we want to measure the viscoelasticity. How is that influenced by asphaltenes? So we use our double wall ring. And you can see, in this case, this very strong viscoelasticity that's produced at the surface of toluene and water in the presence of asphaltenes. On the left, the concentration is 1 meg per mil. And you can see the dark data, those are the elastic moduli, much higher than the open circles, the viscous moduli. And likewise, it's at a higher concentration, those are elevated. So extremely viscoelastic interfaces. So we expect, as we increase the concentration and the aging time, that the coalescence should be delayed. So what do we see? Well, here we see plotted the coalescence time as a function of aging time, and it does go up. Look at the red data. That's at 1 meg per mil. Below that, at 0.066 meg per mil, the coalescence is very fast, just a few seconds. But the red data, you can see it increasing to, it might take up to 10 minutes for the drop to coalesce. And that's a big problem in the desalter. But it goes through a maximum. What's that all about? So we needed to understand the reasons for this maximum. If you go to higher concentration, you still get a maximum, but it happens earlier and earlier. But we did see, you can see here the influence of interfacial viscoelasticity, retarding the coalescence. Why is it going through a maximum? Well, that we needed to do another experiment. And here is the bottom camera. Remember, that will see interference patterns. As we bring the drop down, you can see them forming here. But something else is happening. You see around those tiny, tiny, tiny little droplets, they're about 10 microns. And that was the answer to the maximum. What we saw for the first time was something called spontaneous emulsification caused by asphaltenes. And what we did to nail that down is we did some confocal microscopy measurements by having toluene with asphaltene, but Nile red. Nile red will fluoresce in the presence of oil, not water. And in the water phase, we use fluorescein. Fluorescein does not dissolve in oil. So we used confocal microscopy to scan across the interface. So now you can see on the left, you see the fluorescein signal, in the middle, the Nile red signal, and on the right is just bright field. So by scanning, you can see in the fluorescein a black circle. On the right, that appeared as a red circle. This is on a loop. That is an oil droplet. But once you're above the interface, the Nile red signal, you see a bunch of black circles. Those are water drops. So what we're forming are water droplets on the surface of toluene and water, and those act as a de-emulsifier, and that's why you go through the maximum. So you can understand this, but you really need interfacial rheology to understand the initial, very important retardation in coalescence. That's critical to the success of a desalter. Okay, the last example has to do with engineering interfaces by deliberately structuring the interface. And we do this in collaboration with some people at Berkeley. You see, this strand that has a helical structure, that's a thread of silicon oil in water. But it doesn't contract back up to a spherical droplet. Something's keeping it slender. You can see it slowly compressing. Well, this interface has been structured by a nanoparticle surfactant monolayer combination that creates what's called a Janus particle on that surface, and you get a very, very viscoelastic film. So we have toluene or silicon oil, some oil phase, and in the bottom we've got water. And then in the oil phase we've got a surfactant, which is a chain of PDMS with an amine head group. The amine head group will tether it to the surface, and the PDMS tail will stick out into the oil. In the water phase, we've got nanoparticles, silica particles or polystyrene that swim around gleefully in the water, but they'll bump up against the interface occasionally. And when that happens, you'll get in a strong association with the amine group and of the polymer chains and the particles. So that's where you're creating these Janus particles. They're different on one side than they are on the water side. You get a very viscoelastic film this way. And you can see here 3 vials, all at the same concentration of particles in the bottom, 50 nanometer silica particles in the water phase. And in the oil phase, we've got 3 different concentration of the polymer surfactant. And then these have been emulsified. And you can see these are you get very, on the right, you can see very clearly a very turbid, very stable emulsion. You can see it here. You can blow up the droplets inside that very stable emulsion. You can see all the wrinkles, and that's a direct indication of a very viscoelastic interface. And the droplets retain non-spherical shape for that reason. So surface tension is a useful technique, but it doesn't give you the answer. Here's the surface tension as a function of time, and you can see it generally diminishes over a pure silicon oil water interface. And that takes about 20 minutes to get there. Surface tension, remember, is a thermodynamic quantity. It's mainly giving you the amount of material at the interface. It doesn't give you the interactions. The interactions you get through interfacial rheology. And you can see it here. On the left are the elastic and viscous moduli at the surface, plotted at time. And this doesn't evolve over 20 minutes. It takes hours. And this is for 5% polymer in the oil phase. And then on the right, you can see a strain sweep, and you can see how strong these interfaces are. And you can go almost to a full strain unit before you get softening in this case. So this is how you can engineer an interface. You get a very, very stable emulsion. So in summary, to remind ourselves, interfaces between fluids, these are often non-Newtonian, complex. And this is a result of the fact that these species that are floating around in the bulk will attach to the surface and interact with each other. Interfacial rheology is important to understand both industrial applications as well as biological. So foam stability, emulsion stability, you saw that with the asphaltene problem, protein stability, and biological films. The Boussinesq number is important to understand. Remember, that's the ratio of surface-related stresses to bulk-related stresses. It's controlled by the mechanical size of what's causing the interface. And the beauty of the double wall ring is you have a very slender ring, so you get larger Boussinesq numbers than are possible with other designs. And this is, allows you to convert your commercial rotational rheometer. You need a very sensitive one, using this patented double wall ring design from TA Instruments to do interfacial rheology. And today we looked at applications that started out with biofilms, then we turned to hydrates, interaction of oil and water, and then asphaltene-stabilized emulsions, and then finally how to engineer emulsions with different combinations of surfactants and particles. So it was my pleasure to offer this webinar to you, and I'll be happy to answer questions that you might have. Thank you very much.
Thank you, Jerry, for that really informative presentation. A recorded version of this webinar will be archived and available through the TA Instruments website. We will now begin the question and answer segment of this webinar. Please submit your questions through the Q&A window. We will do our best to answer as many questions as possible.
Okay, so Jerry, we're getting some good questions coming in. So we've had a few questions about some experimental details. So first, can you go back to the double wall ring geometry and describe why that is preferred over a single wall ring?
Yes. The double wall ring geometry gives you a symmetric shear flow on either side of the ring, and so you get double the surface stress. You're going to get much signal. The ring itself is important because remember that to get a large Boussinesq number, the length scale of the flow generating device should be as small as possible, and that's why the ring is used instead of a bicone. So if you're going to use a ring, which is preferred for a high Boussinesq number, then you want to have symmetry on both sides of the ring, and that's provided by the double wall.
Okay, I think that makes sense. There have also been some questions about sample preparation and sample loading. Are there any best practices that you could recommend, or perhaps bad practices that you've seen that should be specifically avoided, or anything along those lines?
Yes. Now, remember there are two types of surfactant systems. There are the soluble surfactant systems and the insoluble. And if it's a soluble system, of course, then the surface active material is already present in the system. And then it's a question of bringing the ring down properly onto the interface. And then slowly, if you are doing a liquid-liquid interface, then slowly, very carefully, and you might use a syringe to do this properly, you might slowly introduce the liquid phase on top to give you that liquid-liquid interface. Now, the placement of the ring right at the interface is facilitated by having a sharp interface, and that's why the ring that's offered by TA Instruments is actually it has a cross section of a sharp diamond, and that helps to pin it to the interface.
Okay. Well, good. That gives some good general guidance. So now we have a question about what maybe is kind of the continuum between surface rheology and bulk rheology, and thinking specifically about the case of biofilms, or maybe in general, how do we understand what the film thickness at the interface is, and is there a way to go from, say, an interfacial shear modulus and some information about the film thickness to some correlation to a bulk shear modulus?
Yes. Well, the measurement of an interfacial rheology is going to respond to an interfacial stress, and it doesn't specifically give you any information about the thickness of that film. And so you could have multi-layers that are presented at the interface. The experiment itself will not tell you that. To understand whether or not that may be happening, you may have to use an optical method to interrogate the interface so that you could determine whether or not you have a multi-layered structure. We've used Brewster angle microscopy in the past to try to determine that. So that it may be necessary to couple the mechanical measurement with some optical method to give you that answer.
Very good. Now we have a question about maybe how we understand the interface between solids and liquids. The specific question addresses measuring partially crystalline fat globules. These fat globules are about 50 microns in diameter. Would this device, or is there another method that you could use to accurately characterize the interface between one of these fat globules and an aqueous phase?
So the fat globule it's residing, is it pinned at the interface, or it's immersed inside water, and we want to measure the mechanics of that fat globule water interface?
Yeah, the fat globule is in an oil-water emulsion. We want to measure the mechanics of that interface between the fat globule and the aqueous system, the aqueous surroundings. That system, as I understand it, and may not be visualizing it properly, would not be directly amenable to the types of rheological equipment that we talked about in this lecture. Okay. So a different method, and it sounds like this is related to, there have been a few other questions about measures of the interface between solid-liquid interfaces. There have been some questions about adhesion and things like that, and those are certainly different, whereas in this case we're looking at really fluid-fluid, whether that be liquid-liquid or liquid-air interfaces.
That's correct. These techniques are really aimed at understanding what I would call mobile interfaces or deformable interfaces,
okay,
as opposed to a solid-liquid interface.
Okay, perfect. Well, I think we have time for just maybe two more questions. So one is a question about the Langmuir trough. The direct question is whether this is a substitute for the Langmuir trough, or maybe you could expand on whether this has been used in conjunction or to be complementary to measurements of a Langmuir trough.
Yes. Well, Langmuir trough is an instrument that allows you to systematically control the surface pressure and phase of a insoluble surfactant system, and you can use that. You can incorporate a interfacial rheology measurement within a Langmuir trough, and Jan Vermont has done that. With the double wall ring system, he has a design of a Langmuir trough that will accommodate a double wall ring, and he has you can find measurements that he's accomplished with that system. So yes, it's a very important way to study the interfacial rheology of the insoluble surfactant systems.
Okay, so it sounds like they complement each other and can sometimes be used in parallel with one another.
Yeah.
And so, and our last question for today is about oil-water, or you talked about oil-water interfaces. Do you see any applications for this in polymer solutions at water interfaces? And would interfacial rheology help to understand how the dissolution might occur through those phases?
You know, that's interesting. I believe that would be certainly possible to get information. Now, you have to be careful if it's a polymer solution what its viscosity is, because remember that we need to keep the Boost and S number large, and so if the viscosity of that polymer solution was excessive, that may make the measurement difficult to carry out. And then, of course, it depends on the amphilicity of the polymers that you're using. Are they strongly attaching to the interface? And of course, that's going to be happening over some period of time. Those are some issues that you'd have to think about and answer before you could determine whether or not you could go forward with that experiment.
Okay, so it sounds like there's some potential there, but certainly some experimental considerations to bear in mind that may be different from some of the other systems that we've studied. So, okay, well, this concludes today's program. I'd certainly like to thank Jerry for spending some time with us today, and I'd especially like to thank all of you and our audience for joining us. This webinar, like all TA webinars, will be archived and it will be available through the TA Instruments website. Please look out for invitations to future webinars from TA Instruments, and be sure to check out our other archived webinars, including the first part, Jerry's first webinar on interfacial rheology, as well as many of our online training courses. Thank you all, and have a great day.
Yeah, thanks as well. Bye-bye.
Thanks, Jerry.